Hi, welcome to another lecture on Calculus 3. Today's topic is double integrals in polar coordinates. We have done double integrals in Cartesian. It's the most common way of approaching calculus, but sometimes Cartesian is not the most suitable system for studying a problem. In problems with circles, cylinders, rotational motion, and such, polar coordinate typically is a more natural choice. So our topic for today is this calculation of this double integral where our region yields itself to consideration in polar. So first we are going to go ahead and refresh our memory about what the polar coordinate was and then come back. So in general, the regions that we are going to look at are bounded by two rays, like these rays you see here, and two curves that are easy to describe in a polar fashion, meaning radius is given in terms of the angle in an easy way. We are going to see how to describe dA, the element of area, by the regions that are bounded by rays and circles. We are going to have an expression for dA, and then we are going to see how to convert from Cartesian to polar and perform the integration. The iterated integral system that we are going to use is going to be same as before. It would not be any different. It's just transformation between one and another is the main topic that we are looking at today. Okay, so let's go after the review of polar coordinates. What was a polar coordinate? So suppose we have choose my pen here. So we have Cartesian. So our Cartesian, as usual, the x, y coordinate system is present. Uh, So if you have a point here, you describe it with an x and a y. But if you want to describe it with the polar, your favorite variables are the distance from the origin, which you call r, and the angle that you make with the x-axis, which is theta. If you remember, going in a counterclockwise in mathematics is considered positive. Going clockwise is considered negative. And the relationship between r and theta, so we are going to describe this point by two sets of coordinates. One is r theta, and the other one, perhaps we'll write it in blue, x and y. So x and y, of course, this is y that we are after, and this is the x, and the relationship between the red and the blue. So these are easy relationship. We have y is hypotenuse times sine of the angle, opposite angle. So y is r sine of theta, and x similarly is hypotenuse, which is r times cosine of theta. So these are relationship that takes us from uh, polar to Cartesian. Going the other way, we have a bit more complicated formulas. We have r squared is equal to x squared plus y squared. Uh, we can take square root, and r can be positive or negative. And if I take a ratio of these two formulas that I had, then I'll have tangent of theta is equal to y over x. And then I can find theta itself. Again, the angle theta can be obtained up to a multiple of pi. So there's a bit of complication in both of these relationships that we had. We might come across some of that issues later on. But these are the straightforward conversion formulas that we have to take us from one to the other. Next issue is, well, in Cartesian, we would describe our element of area, or dA, in terms of a change in x and a change in y. So we had uh, in the Cartesian, when we want to talk about the element of area, the most comfortable description of this would be to consider a rectangular region whose dimensions are dx and dy. However, in polar, well, before we get to polar, let's see what is it that's so comfortable about this rectangle. This rectangle is specified by having y equal to some number at bottom and the top. So this could be y is equal to some y1, and this is y is equal to some y2. That is how we are limiting the rectangle. And then x equal to x1 and x equal to x2 are the left and right walls of this region. uh, well, how do we define a region for ourselves in polar? The idea is very similar. Remember that when we have a polar coordinate, if I say r is equal to a given number, so suppose I tell you r is equal to 2, well, what does that mean? It means the radius of a certain circle is equal to 2. So r equal to 2 would be something like that. If I talk about another radius, r equal to 3, well, that's going to be perhaps a bigger circle. So similar setting, we have a second circle. Well, how about the other coordinate value? Suppose I specify a value for theta. Say I say theta equal to pi 6. So theta equal to pi 6 would be something like this. Theta is equal to pi 6. If I talk about some other angle, well, let's say theta equal to pi third. This is going to be the line where theta is some other value pi third. Now, in terms of having a region, here we had this kind of a rectangle, which is limited by x and y's. But now I have this region, which is doesn't have a specific name, but it kind of looks like a trapezoid, except that two edges of it are round pieces of a circle. That is the element of area for us in polar, and we want to describe this element dA here instead of the dA that we had before. So element of area now is between two radii that are close to each other, like one of them is at r and the other one is r plus dr, and the two angles also are close to each other. So what does that mean? Suppose I have so I consider a circle, this is r, and then I slightly increase the radius. Of course, now if I make it very small, I might have a hard time seeing it, so I'm going to exaggerate this. So this is the next one is going to be r plus dr, that is the enlarged circle. Similarly, we are going to have some angle theta as one ray, and the nearby angle is going to be theta plus d theta. So the region we are going to look at might look like a rectangle, but of course it isn't. The two sides of it are circles, and the other two are not parallel either. So it's a special shape which we are going to use as a basis. So this is going to be this special region is going to be the dA for us in our problems. So our first task is to go ahead and find out how does dA relate to these quantities that we have. So I have a r, I have a dr, I have a theta, I have d theta, and the question is, how do these four things combine with each other to give me an element of area? So let's go ahead and see how does that work. Okay, what I'm going to do next is to show that this element of area in polar is going to be r dr d theta. So this this element of area that has this particular shape here is going to be the product of these three items, dr, r itself, and d theta. Let's see how. It's a very simple derivation based on the area of a circle that you remember from middle school. Essentially, that quickly is going to give us what we are after here. So, what do you remember about the circle? If you have a circle of some radius r, what is the area of it? Area of this, area of the circle is of course r squared, pi r squared. Is that right? So area of a circle is now suppose I'll want the area of a sector of this circle. Suppose this is an angular sector theta, and I want to find this area. Very simple. We say going around the circle in a full circle, the angle is 2 pi radians. And 2 pi radians, the area that we get is pi r squared. So half of that angle, half of this central angle 2 pi times r squared. So if my angle is theta, what would be the area of that? It's going to be, of course, half of that angle multiplied by r squared. So this was area of a circle, the entire circle, but now the area of a sector, is going to be 1/2 r squared times theta. Now we are going to do the following. Suppose I have a circle of, say, radius r1, and then another bigger circle of radius r2. So this one's going to be r2, and I'm after the same kind of area, this trapezoid looking thing. How do I find the area of this one? Well, I get the area of the big slice and subtract this area of the small slice out of it. So 1/2 of r2 squared times theta. So this central angle is still theta. That's the area of the big slice. So the big slice would be that one. So that is 1/2 area of that one is 1/2 of its radius squared times theta. Then from that I subtract the area of the smaller slice. What is that one? Well, minus 1/2 of r1 squared theta. Well, let's factor this. I can of course factor 1/2 r2 squared minus r1 squared times theta. Well, I can write this thing as 1/2 of r2 plus r1 times r2 minus r1 times times theta. So what is this? 1/2 of r2 plus r1. That would indicate an average radius. So average radius is somewhere here. That's the average of the two radius. R1 and R2, their average will be equal to that. So that is average radius, and this is what is that? That is the difference of the two radius. So suppose R2 and R1 are close to each other. So as we go from one to the other one, the difference is going to be what will be the increment in R. So increment in R we are going to show by dr. This is a change in R. The average of two radius, well, the big radius and the small radius, the average of the two of them is somewhere in the middle of the two, and that we can write it as R. If the angle that we are dealing with is a small angle, we better write it as d theta. So element of area then, element of area which has a central angle, small d theta. We have to make it small so that we let our integration work. And then the difference in the radii is going to be dr, and the radius itself is going to be r. So that's the element of area. So without further ado, we have element of area is r dr d theta. Next question is, well, how do we give a description of the region of the integration? Typically, in polar coordinates, description of curves are given. So we might have some sort of a curve here. In Cartesian, it was the main players were x and y. Typically, y is given in terms of x and so on. In polar, the common way of handling this is r is given as some function of theta. So r perhaps equal to, let's call this g of theta. That could be one end of the region that you have. Perhaps we call it g1. Then we might have another curve that lays out the outer boundary of the region. So that could be r is equal to g2 of theta. Then for our angle, typically we start at a particular angle. Let's call it theta equal to theta 1, and then we go as far as certain other angle. Sorry. Let's see what happened. So we have, we have another angle theta equal to theta 2, and the region that we typically consider in polar is a region of this style. So r is given in terms of theta. There is an inner radius and outer radius, and there is a beginning angle and the ending angle, and then there are formula then in the double integral that they had with f of x and y dA over some region r. So the region r is, this is the region r we are interested in. We rewrite this thing in the following way. The x and y are going to be transformed according to these formulas. And then, so we have double integral. So f of, instead of x, we have r cosine theta. Instead of y, we have r sine theta. Instead of a, we have r dr. And then, then d theta. R goes from the inner wall, which is g1 of theta, goes to the outer wall, which is g2 of theta. And then our angle in theta at the end, it goes from the starting angle to the ending angle, theta 2. So we do the substitution for x and y, we do the substitution for element of area, and then we perform the integral exactly as before without any change in that procedure itself. So let's go ahead and do an example of this type. Okay, let's go take a look at a problem. Suppose we have a surface defined by an equation in x and y, and we want to find the area under it over a certain circle. Let's go ahead and take a look at this one. So here I have a surface given by easy formula, z is equal to 1 minus x squared minus y squared. So it is a paraboloid on top of the xy plane with the height of it at z equal to 1. I want to find the volume under this under the surface and above the unit circle. Unit circle. So to describe that, we have, of course, a unit circle somewhere underneath this dome, and there is a kind of a cylinder that extends from there, and then the top of this cylinder is kind of bulging out in the shape of this it's bulging out in the shape of this paraboloid. We want to find that volume. So how do we write the volume? Our f is, this is going to be f. This is going to be f of x and y is given by this height. Well, what is the easy way of writing this in polar coordinate? So I say I convert f of x and y to f of r cosine theta and r sine theta. So what is that? It's going to be 1 minus r cosine of theta squared, and then minus r sine of theta squared. So of course that is 1 minus, I can factor r squared out of cosine squared and sine squared, and that conveniently just boils down to 1 minus r squared. So my f turned out to be a very friendly function. Then what? Then I have to do this integral. Previously I would have written the integral as double integral of f of x and y dx dy, or just dA. Now I'm writing it as instead of that f, I write 1 minus r squared, and instead of this element of area I will write r dr d theta. Well, the unit circle extends from r equal to 0 to r equal to 1, and it's also convenient that the theta goes around the entire circle at 0 to 2 pi. We learned in the lecture a while back that if your function separates to r and theta, you can actually perform the integral very conveniently. Integral for theta 0 to 2 pi, you can separate it from the integral from r equal to 0 to r equal to 1 of r times 1 minus r squared dr. So integral of theta d theta is just a theta that has to be evaluated between 0 and 2 pi, and integral of well, this is r minus r cubed, and the antiderivative of that is r squared over 2 minus r to the power of 4 over 4, and you're calculating it between 0 and 1. So the angular contribution, first component is 2 pi. The second one is 1/2 minus 1/4, and that is of course boils down to just 1/4. 1/4 times 2 pi, and we get pi over 2. So the volume under this dome from the xy plane to the surface itself, limited on a cylinder which is built on top of the unit circle. That volume turns out to be pi over 2. Now you need to do a few more problems of this type, and that's going to get you ready for more problems in polar coordinates. Okay, so what did we do today? We had this particular region where the boundaries are defined by fixed values for the radius and the angle. So our typical grid is has this polar shape to it, and our element of area becomes a region that looks like a kind of a trapezoid with the top and bottom of it being sectors of a circle. So we described how to calculate the double integral in this setting by showing that instead of x and y, you'll have r cosine and r sine theta, and instead of the element of area dA, we have this important formula here, which is dA is r dr d theta. That is the main contribution of this lecture. So we did one example with a paraboloid on top of the unit circle, and we found the volume underneath that dome pi over 2. Until next time, good luck and God bless.